Hello and welcome to our next module on cyclic codes. Let's start with a quick outline for today's lecture. We will start looking at the details of cyclic codes, how to construct them, how to look at their properties. We will introduce the notion of generator polynomial, the syndrome polynomial, and finally move on to the matrix representation. Please recall that cyclic codes are a subclass of the linear block codes. But first, let us have a very quick recap as to what we have studied so far. We have talked about rings and fields and polynomials and how these mathematical tools help us construct cyclic codes. We have seen what is a cyclic code. Let us redefine it for clarity. A code C is cyclic if number 1, C is a linear code and any cyclic shift of a valid code word also results in another valid code word. So, if A0, A1 dot dot up to n minus 1 is a valid code word, then a cyclic shift means an minus 1 comes in the front and then each one gets shifted by 1 to the right, and that is also a valid code word. So, if you see, the first point says that if this is a linear block code, then cyclic code is a subclass. All that we have studied regarding linear block codes holds true for cyclic codes, but we have introduced an additional algebraic constraint, that is the linear cyclic shift of any valid code word is another valid code word. Consequently, this is a subclass and it is a much stronger code. We have looked at some examples in the last lecture, and here is a quick one. We have a valid cyclic code here with 4 code words, and if you can quickly verify it is a linear block code, the all 0 code word is a valid code word, then sum of any 2 code word gives another valid code word, and more importantly any cyclic shift also results in a valid code word. We then introduce the notion of polynomials and why they are important. Polynomials in general are represented as follows: f(x) is equal to f0 plus f1x plus so and so forth till fm x raised to power m, where fm is called the leading coefficient and m is called the degree of the polynomial. If fm, which is the leading coefficient, is 1, then it is a monic polynomial. We also looked at the division algorithm, where you find out that for a pair of polynomials ax and bx, where bx is not equal to 0 in fx, fx is a set of polynomials, then you can have a unique pair of polynomials qx and rx, which are nothing but the quotient polynomial and the remainder polynomial, such that ax is equal to qx times bx plus rx, where degree of this remainder polynomial must necessarily be less than the divisor b of x. So, we did this example, and sometimes we also called the remainder as the residue. And 2 important properties that we will use frequently are that the sum of 2 polynomials, the residue of it is the sum of the residues, and similarly we have a property for the product of 2 polynomials. We have seen that polynomials can be added, subtracted, multiplied and divided, and it is seen that the coefficients follow the Galois field over which the arithmetic is carried out. So, please note that ax, bx and fx are defined over some Galois field, and it is important because multiplication, addition, division all will change, because if the Galois field changes, the arithmetic changes. We then introduce the notion of irreducible, which is akin to whether it is a prime polynomial, whether you can factorize it or not. So, we found out that if a polynomial f of x is contained in the set of polynomials capital F of x is said to be reducible if it can be written as a product of 2 polynomials, right. So, you can factorize f of x, but this product follows the rule of the Galois field over which we carry out the multiplication. So, it is possible that some f of x is reducible in some Galois field, but irreducible in another Galois field. And if the irreducible polynomial also happens to be monic, that is the leading coefficient is 1, it is also called as a prime polynomial. We also introduced the notion of a field, where the ring capital F of x by f of x is a field if and only if f of x is a prime polynomial in f x. So, we looked at this example p of x, it is a prime polynomial and we can construct a field G F 8 with 8 elements using this p x. Please note that when you carry out capital F of x divided by small f of x, and in this case we are putting at p of x, then the residues, all the remainders have a degree 2 or less. So, if the degrees are 2 or less, then we have 8 distinct polynomials here. We made some observations. First and foremost is that if you have x n and you take it mod x n minus 1, it equals to 1. So, we will use this term modulo x n minus 1, that is, this is a polynomial, and we will divide our products, additions, etc. by x raised by n minus 1, and whatever is the remainder is what we will deal with. So, x n, x raised by n, when you do modulo x n minus 1, it is unity. Please note, we also observed that a code word can uniquely be represented by polynomials. This is how we connect our polynomials to code words. For example, if your code word is C1, C2, C3 up to Cn, and you can write it as Cx is C0 plus C1x and so on and so forth. So, the code word can be C0, C1, C2 up to Cnx. For example, C is equal to 207735, this is my code word, and I have an equivalent polynomial representation as 2 plus 7x squared plus 7x cubed, so on and so forth. So, 2 corresponds to the first coefficient, 0 corresponds to the missing 0 into x, so that we do not write, and then 7x squared corresponds to the third. So, in a way the degree of the x, the power of x actually represents the location of the coefficient, and these coefficients can belong to the Galois field under consideration. Here it is G F 8. So, why are we looking at polynomials in the context of cyclic codes? First observation is, if you multiply any polynomial by x, it tantamounts to the cyclic right shift of the code word elements, because you simply raise the power of x by 1 for each one of the x's. So, if you had Cx as C0, C1x and so on and so forth, then x into C of x is nothing but C0x plus C1 x squared plus C2 x squared. Each x has gone up, but now your x raised to power n is the highest power, but my Cx, if it were to represent a code word, should have the highest power x raised by n minus 1, because there are n elements from C0 up to Cn minus 1. So, in order to put this last coefficient in the front to make it a cyclic code, we have to take modulo x n minus 1. So, just the operation of taking this polynomial, and if I divide it by x raised by n minus 1, I simply get this Cn minus 1 in the front, and my cyclic shift operation is complete. So, there are still n elements in my code word, but they have all undergone a cyclic shift. So, please note we have used this property. So, any polynomial modulo x n minus 1 can be reduced simply by replacing x raised by n by 1, x raised by n plus 1 by x, and so on and so forth. So, we have redefined cyclic codes. Cyclic codes in Rn is a cyclic code if and only if C satisfies the condition that this collection of polynomials capital F of x divided by f x is in Rn. So, if Ax and Bx are two polynomials belonging to C, so suddenly we are talking about polynomials as element of a code. No problem, because polynomials have a 1-to-1 correspondence with code words. So, if two code words belong to C, I can equivalently state that Ax, which corresponds to code word 1, and Bx, which corresponds to code word 2, they both belong to C. And consequently, sum of 2 any code words, here in this case code word polynomials, is also in C. Similarly, if I take Ax and take any other polynomial Rx and then I multiply them, then also we get it as a valid code word. We then looked at how to generate cyclic codes, and the steps are given as follows. Take any polynomial f of x in Rn and obtain a set of polynomials by multiplying f x by all possible polynomials in Rn. The set of polynomials obtained above correspond to the set of code words. So, basically we have some kind of a notion of a generator polynomial, and the block length will be n. So, let us now formally introduce the generator polynomial. Let C be an n comma k non-zero cyclic code in Rn. Then there exists a unique monic, this is important, unique monic polynomial g of x of the smallest degree C. That is, there could be many polynomials which can do the job, but we are talking about the one with the smallest degree, and that we define as g of x. The cyclic code C consists of all multiples of the generator polynomial g of x by polynomial of degree k minus 1 or less. And most importantly, g of x is a factor of x raised by n minus 1. Now, this is probably the most important observation here. If we state that g of x is a factor of x raised by n minus 1, that means we have now a recipe to create all possible cyclic codes. All we have to do is factorize x raised by n minus 1 in the appropriate Galois field, and each factor is potentially the generator polynomial of a cyclic code. So, all we have to do is learn to factorize x raised by n minus 1, and we have the valid generator polynomials. So, let us look at these 1, 2, 3 properties, and we will try to see whether we can prove them quickly, and we will look at it intuitively. So, number 1, there is a unique and monic polynomial g of x of smallest degree. Number 2, that if a cyclic code C consists of all multiples of the generator polynomial g of x by polynomials of degree k minus 1 or less. So, if I multiply g of x with any arbitrary polynomial of degree k minus 1, then I get a valid code word polynomial. And finally, the most important one, g of x is a factor of x raised by n minus 1. So, let us look at 1, 2, 3 individually. So, number 1 says that there exists a unique monic polynomial g of x of the smallest degree C. So, to prove or disprove this, we have to see that suppose both g x and h x are monic polynomials in C of the smallest degree. Fine. I mean, either this is true, or g of x and h of x have been able to find one more candidate, and then it will no longer be unique. Then g x minus h x is also in C. Why? Because g x is a valid polynomial. You multiply it with 1, it should give itself, and any multiplication with a polynomial of g x should give you a valid code word polynomial. So, g of x valid and h of x is another candidate. So, the difference of these two should also be a valid code word polynomial. Therefore, we say that g x minus h of x is also in C. But please note, both of them are monic, and if you subtract them, then the degree goes down, and therefore, we violate this smallest degree constraint. So, this gives a contradiction. We now look at point number 2. The cyclic code C consists of all multiples of the generator polynomial g of x by polynomials of degree k minus 1 or less. So, let us say a of x is an element of C, all right. So, it is a valid code word polynomial. Then we know that a of x can be always written as some q of x, quotient polynomial, times g of x plus r of x, where degree of r of x should necessarily be less than g of x. So, we can always write it like this from the division algorithm. But if you flip it around and put r x, then r x is nothing but a x minus q x times g x, right. But this r x must be an element of C, must be a valid code word polynomial. Why? Because a x we started off with a valid, g of x and q of x, right. So, they are also valid code word polynomials, but the degree of g of x must be minimum amongst all code words, right. But this is only possible if r x is 0, and consequently a x must be equal to some polynomial q of x into g of x. So, that means multiplying g of x by some arbitrary polynomial q of x should be equal to a of x, the valid code word polynomial. Okay. So, for a code defined over g of q, there are q raised to power k distinct code words, and these code words correspond to multiplying this generator polynomial g of x with the q raised to power k distinct polynomials q of x, where degree of q of x is less than k minus 1. So, in this way we show that I can generate the entire code space by simply multiplying my g of x with any arbitrary polynomial of degree k minus 1 or less. We now look at the third property, g of x is a factor of x n minus 1. So, by division algorithm, x n minus 1 should be written as some q of x times g of x plus r of x, where the degree of this remainder polynomial should be less than the degree of g of x, right. But you can again take it on the other side, and r x can be written as x minus 1 minus q of x g of x, again modulo x raised by n minus 1. But if you take it, it comes out to be minus q x g x. But please note, q of x is a polynomial, minus q of x is also a polynomial. So, if you multiply it with g of x, we also end up getting another valid code word polynomial, hence it is an element of C. But then we have quickly generated a code word r of x whose degree is less than that of g of x by this, right. And this violates the minimality of degree of g of x, which we showed earlier, unless r of x is 0, which means if you put r of x is 0 here, then x raised by n minus 1 can always be written as the product of g of x times some q of x. Consequently, g of x must necessarily be a factor of x raised by n minus 1. Okay? And therefore, it's you factorize x raised by n minus 1 and you get q x times g of x. G of x is definitely a generator polynomial of cyclic code, and so is q of x, because it itself is a factor of x raised by n minus 1. So, we tried for one and we got the other one free. So, a cyclic code C may contain polynomials other than the generator polynomial, which can also generate C. So, but the polynomial with the minimum degree is called the generator polynomial. This we had mentioned earlier, and the degree of g of x is n minus k, and therefore, when you multiply with another polynomial of degree k minus 1, you get a resultant polynomial with a degree n minus 1. So, if you look at it, we can write it. So, we say that any code word polynomial c of x is nothing but some arbitrary polynomial a of x times g of x. But please note that this is a code word polynomial. So, its degree is n minus 1, because the degree n minus 1 states that I have got c 0 plus c 1 x plus c 2 x squared plus so and so forth to c n minus 1 x raised by n minus 1. So, I have from here c 0, c 1, c 2 up to c n minus 1. So, I have a linear block code of block length n. So, degree should be n minus 1. Now, if you look at this polynomial, the degree here should be k minus 1, we just now saw. And here, in order to ensure that the degree here is n minus 1, here the degree should be n minus k. Therefore, the product of a polynomial with degree k minus 1 and degree n minus k, so these would add up and you would get a polynomial of degree n minus 1. So, consequently, we should be able to write in general g 0 plus g 1 x plus g 2 x squared and so on and so forth till g n minus k x n minus k. So, we come back to our slides and we note that degree of g of x is n minus k. Let us do a quick example to understand what we did so far. Suppose we have to find all binary codes of block length 3. So, block length 3 means n is equal to 3. So, we have to factorize x raised by n minus 1, where n is equal to 3. And which Galois field should we consider? Binary code means GF2. So, two things are important. The block length must be fixed, otherwise we do not know what x raised by n, what does n mean. And once we have to factorize, we definitely must know where do we do our math. So, we need to know the Galois field. So, given the block length and the Galois field, we are ready to go. So, we have to factorize x cubed minus 1 over GF2. So, if you factorize it, you get these 3 generator polynomials. These are the 3 factors that you can write out, because you can write x cube minus 1 is equal to x cube plus 1, simply because over GF2 1 plus 1 is 0. So, 1 is equal to minus 1, all minus signs can be replaced by plus signs. So, x cubed plus 1 is equal to x plus 1, x square plus x plus 1. So, it is actually 1 is always a factor, x plus 1, x square plus x plus 1. So, I have got 1. Well, 1 is also a valid generator polynomial, because it is a factor of x raised by n minus 1. 1 is a factor of everything, but it gives a trivial code. It gives really 0 0 0 0 0 1 and so on and so forth. If you must be a purist, you can verify that this is a linear code and it is also a cyclic code. Any cyclic shift is a valid code, but this is really a trivial example. It has no interesting properties. But then you look at factor x minus 1. This one leads to the code 0. So, one of the polynomials. If you look at x minus 1, it will give you these 4 codes, polynomial code words, and if you have x squared plus x plus 1, you have got these 2. So, this is a repetition code. So, x squared plus x plus 1 is a generator polynomial for a repetition code of block 3. Now, x cube plus 1 itself is a factor, and so this again gives a useless code. So, let us see how we use g of x. So, as we have mentioned, any code word polynomial can be generated using an information polynomial I of x and a g of x. Now, since any vector can be effectively represented as a polynomial, the error vector can also be represented as an error polynomial. So, when we send our valid code word through an error prone channel, we receive sometimes a received vector which is not the same as c of x. In fact, we receive v of x as c of x plus an error vector e of x. So, any sequence of bits which can be represented as an error sequence can be represented also as an error polynomial. Now, we introduce the syndrome polynomial. Please note, syndrome decoding was very much a part of linear block codes, and here we have just the parallel definition. So, we define the syndrome polynomial s of x as the remainder of nu x under the division by g of x. What does it mean? If you have s of x as the syndrome polynomial, you take the received vector nu of x and divide by g of x, whatever is the remainder is the syndrome polynomial. And if you can write it explicitly, it is r g of x, which is you are taking the remainder with respect to g of x. And what is v of x? You send the valid code word polynomial c of x plus e of x, but it can be represented using this properties of residues as r g c of x plus r g e of x. But we know that whenever we divide a valid code word polynomial by a generator polynomial, you get 0. Okay? It is a perfect multiple. That is how you generate a c of x. So, this first term goes out of the window, and what you get is r g of x e of x. Okay. So, let us look at a quick example. Consider a generator polynomial g of x is equal to x squared plus 1 for a ternary cyclic code over g f 3. So, first thing that we need to verify is whether this g of x is indeed a factor of x raised by n minus 1 over g f 3, but for that I need to know the block length n is equal to 4. So, first thing we need to do is, can we actually factorize x raised to the power 4 minus 1 over g f 3, and we should be able to get g of x is equal to x squared plus 1 as one of the valid factors. All right. So, well, it really is quite obvious, because I can take x raised to the power 4 minus 1 equal to x squared plus 1 into x squared minus 1. So, clearly x raised to the power 2 plus 1 is indeed a factor. So, we have cyclic codes here, n is equal to 4, k must be 2, because the degree of g of x is n minus k. So, n minus k is 2, n is 4, so k must indeed be 2. So, what we are trying to look at is a 4,2 cyclic ternary code. Okay? This is what we have set out to do, to construct a 4,2 cyclic ternary code with this generator polynomial g of x given as x squared plus 1. Now, if it is ternary and k is equal to 2, then there are total of q raised to the power k valid code words. Q is 3, k is 2. So, there are 9 code words in our lookup table. This is what we are looking at. So, if you write out the table using the generator polynomial, you take g of x and take all possible I x, which is information polynomials of length k. So, I is equal to 0, 1, 2, all right, because it is a ternary, x, x plus 1, x plus 2, 2x, 2x plus 1, 2x plus 2. These are all possible polynomials of degree k minus 1 or less. What is k? K is 2, k minus 1 is 1. So, degree 1 or less. So, this is all I can do. All right. So, explicitly, if you want to see, you are looking at your I of x, and I of x can have degree k minus 1 and therefore, I have got 2 places to fill, and this first one can be 0, 1 or 2, and the second place can also be 0, 1 or 2, and therefore, we have 9 polynomials, and these would correspond to 9 code words. These are clearly information polynomials, and this is the lookup table. So, if you go back, you have everything starting from 0, 0, 0, 1. Please remember, we have k equal to 2, and we are working at GF3. So, we have 0, 0, 0, 1, 0, 2, and we can go right up to 2, 1 and 2, 2. And on the other hand, when we have the code words C, there we look at 0, 0, 0, 0, because n is equal to 4, and we are looking at 4, 2 cyclic code. So, you get 0, 1, 0, 1, and you go right up to 2, 1, 2, 1 and 2, 2, 2, 2. So, we come back to our slide and look at the entire table, and we make a very interesting observation. This cyclic code has done nothing but repeated the first 2 symbols one more time. So, 0, 0 becomes 0, 0, 0, 0, 0, 1 becomes 0, 1, 0, 1, 1, 2 becomes 1, 2, 1, 2. So, it is in some sense some kind of a repetition code, just repeating the entire block, information block one more time. Looks to be pretty trivial, but we have to see whether it is a useful code or not, or whether it is just a toy example. But first note that it is a valid cyclic code. Sum of any 2 code words is another valid code word. You can do that math. It is over GF3. So, modulo 3 arithmetic can work. So, if I take for example 0 2 0 2 and add it up to 1 0 1 0, I get 1 2 1 2, which is present right here. Or if I can take 2 1 2 1, add it up to 2 2 2 2, 2 plus 2, you can do a math for 1. So, 1 0 1 0, which is another valid code word right here. So, you can check that sum of any 2 code words is another valid code word. All 0 code word is present. So, it is definitely a linear block code, but most interestingly, any cyclic shift of a valid code word is another valid code word. So, it is indeed a cyclic code that has been generated using this generator polynomial x squared plus 1. So, we continue with this example, and to our dismay we find that the Hamming weight is 2. See, Hamming distance and Hamming weight should be the same because it is a linear block code. So, I just pick up these 2 candidates 0 1 0 1 or 0 2 0 2, 2 non-zero elements. So, weight is 2. So, clearly your Hamming weight for this minimum weight for this linear block code, which is cyclic, is 2. So, d star equal to 2 means at best it can detect 1 error and correct 0 errors. So, is it useful? So, we make another observation. We observe that the code word polynomial, if it is valid, should be divisible by the generator polynomial. Therefore, possibly we can detect more number of errors than suggested by our minimum distance calculation. How is that? So, assume that g of x is being used as a generator polynomial, and without losing or without loss of generality, we can say that the transported code word is an all 0 code word. It is a linear block code. So, you can always do an example with an all 0 code word and generalize it. So, the received word is nothing but the error polynomial, because C of x is 0, we are sending the all 0 code word. So, the received vector is the E of x. Now, in order to detect, please note we are talking about the detection problem, not the correction problem. We want to detect whether there is an error or not. So, detection will require us to divide the received vector by g of x, that is to divide E of x by g of x. Now, if it is a 0, then we get the conclusion as it is a valid code word, even though E of x is an error. Or if we look at the E of x carefully, if it has odd number of terms, then no matter what you do, division by g of x, which is only 2 terms, will leave behind 1 term. It is just basic division. In order to cancel out all the terms of E of x, right, we should have an even number, because each time g of x, when I divide, I cancel out, I try to cancel out 2 of them. So, if you have E of x containing odd number of terms, I will always end up with a non-zero answer, regardless of how many such terms are. But please note, each term corresponds to one error. So, we are actually going to possibly detect more number of errors than one as suggested by the minimum distance. Let us carry this example forward. So, suppose we have 3 errors. Okay. So, the error polynomial looks like x cubed plus x plus 1. It means that the error is at location 1, location 2 and location 4. Please note it is a 4, 2 code word. So, there are 4 locations for error to happen, because the code word is of the length n is equal to 4. So, here we have 1 1 0 1 is the polynomial corresponding to this error vector. So, we have the cyclic code g of x is equal to x square plus 1 and d star is equal to 2. So, even though theoretically it seems we can only detect one error, if we try dividing E of x by g of x, we will get a remainder, a non-zero answer, and consequently we will raise a flag and say that yes, indeed we have detected an error. So, the theory says that not more than one, sure 2 errors can never be detected, but 3 errors, yes, it can detect, 4 errors probably not. So, this gives us a glimpse as to how strong we can make our error control codes in terms of using cyclic codes in terms of detecting errors. So, again we are talking about detecting, not correcting. So, they can be used for checks, most likely we call them cyclic redundancy check. So, CRC codes are very popular in detecting errors. So, we now shift gears slightly and we come back to our original flavor of linear block codes. If cyclic codes are indeed subclass of linear block codes, then we should be able to represent them in terms of a generator matrix. So, we have a standard way to represent a generator matrix for a cyclic code. Please note the structure. So, G0, G1 up to Gr and so on and so forth with one cyclic shift and so on and so forth, and we have k rows and n columns. So, please note that the n minus r rows of the matrix are linearly independent because of the echelon form of the matrix. Please note that. Okay. So, it is a simple observation. So, they are linearly independent, and these code words are actually, the rows are actually the code word. How is that? Well, g of x is always a valid code word polynomial. So, the corresponding vector which is g0, g1, 0 up to n. So, the length is n, but the degree of g of x is n minus k. So, there r goes up to n minus k only. Okay. So, we have the first one as a valid code word, the second one is one cyclic shift, third one is another cyclic shift, up to k cyclic shifts, and that constitutes my entire generator matrix. So, we can write that g of x valid, x g of x another valid code word, x square g of x of course it is a cyclic shift by 2, and so on and so forth, and sum of any two of them, each one is a valid code word, is also valid code word. So, indeed g of x and all of its cyclic shifted versions which form the rows can generate the entire code space. So, indeed we have c of x is q of x times g of x for some polynomial q of x. So, we are explicitly writing that any polynomial times g of x can be written as sum of shifted code words, and therefore, you can prove that the matrix G is indeed a generator matrix, just because the rows are valid code word polynomials. And we know that the dimension of the generator matrix is k cross n, and the degree of g of x is n minus k as we established. So, with that we come to the end of this lecture. So, let us quickly summarize what we have read so far and studied. So, we have looked at cyclic codes in more detail. We have introduced this interesting concept of a generator polynomial, what should be its degree, why it generates the entire code space, and then we looked at syndrome polynomial and why it is possible to detect more number of errors than predicted by the D star philosophy. And finally, we looked at the matrix representation, and this is where we will continue in the subsequent lecture. We also looked at some examples to show that yes, it can indeed do better than the error detection predicted by D star. With that, we come to the end of this lecture.